Hello, my friend, and welcome to Orbital Dreams. There is something strange about a magnet. It moves things without touching them. It gives empty space a direction. And if you follow that simple mystery far enough, it leads from a refrigerator door to Earth's hidden core, from glowing auroras to storms on the sun, and eventually to magnetars, the strongest magnets known in the universe. But tonight, there is no need to chase these ideas quickly. Let the day loosen its grip. Let the noise in your mind become softer, the way iron filings slowly settle into invisible lines around a magnet. For the next little while, you can simply rest here, while we explore a quiet force that has been shaping the universe all along. Tonight, we'll follow magnetism from something ordinary and familiar into something vast and cosmic. We'll ask how an invisible field can move matter, protect a planet, paint the sky with light, and reveal that space itself is not as empty as it seems. So settle in, breathe slowly, and let the world become a little quieter. Chapter 1. The invisible force in your hand. A simple magnet may be one of the quietest ways to feel a fundamental power of the universe resting directly in your hand. At first, it hardly seems dramatic. A small magnet on a refrigerator door, a compass needle turning softly toward the north, a metal paperclip suddenly leaping across a table as though it has heard a silent call. Nothing explodes. Nothing glows. There's no sound, no smoke, no visible beam between the objects. Yet something real is happening in the empty space between them. The magnet is reaching outward through a field, and the field is shaping the motion of matter. That is what makes magnetism feel so strange. Most forces in everyday life seem to require contact. You push a chair, lift a cup, close a drawer, or press your hand against a wall. Your body expects the world to answer through touch, but a magnet works before touch begins. Bring it near a piece of iron, and the iron can respond while a small gap still separates them. The space between the two objects seems empty, yet it is already active. Something invisible is present there, organized enough to pull, twist, or guide. This invisible influence is called a magnetic field. A field is a way nature fills space with possible action. It does not need to be seen in order to be real. Gravity is also a field. You cannot see Earth's gravity wrapped around you, yet every step you take depends on it. In the same quiet way, a magnet creates a magnetic field around itself. The field extends outward, weakening with distance, but still forming a real structure in the surrounding space. When the right kind of material enters that structure, the material feels a force. This is why a magnet can seem almost magical, especially when we first encounter one as children. A small object pulls another object without a string. Two magnets push each other away as though an invisible cushion has been placed between them. A compass needle turns again and again toward a direction no hand has chosen for it. The mystery is real, but it is not magic. It is matter behaving according to deep physical rules. The story begins inside atoms. Every solid object around you is built from atoms, and every atom contains electrically charged particles. Electrons, which carry negative charge, are especially important for magnetism. Their motion and their intrinsic quantum property called spin give them tiny magnetic effects. In many materials, these tiny effects point in many different directions. They cancel one another so completely that the object, as a whole, does not behave like a magnet. A wooden table, a cotton shirt, a glass of water, and most stones do not pull paper clips because their internal magnetic effects are balanced in ordinary conditions. Some materials are different. Iron is the most familiar example. Nickel and cobalt behave in a similar way, and certain alloys can do it too. In these materials, groups of atoms can line up their tiny magnetic effects together. These groups are called magnetic domains. A domain is like a small neighborhood inside the material where countless atomic magnets are pointing in the same general direction. In an unmagnetized piece of iron, many domains may point different ways, so their effects still mostly cancel out. But when enough domains become aligned, the material begins to act as one larger magnet. A permanent magnet is a material in which many of these domains remain organized. Its internal order gives it a north pole and a south pole. These names are useful labels for the two ends of the magnetic field, though the field itself is continuous. The field curves outward from one region of the magnet and loops back toward the other. If you have ever placed iron filings near a magnet, you may have seen them arrange themselves into graceful arcs. The filings are not creating the field. They are revealing a pattern that was already there. This idea is important because it changes the way we imagine empty space. The air around a magnet does not look different from any other air. Yet if iron filings, a compass needle, or another magnet enter that region, the hidden pattern becomes visible through their motion. Space is not simply a blank container where objects sit. Around a magnet, space has direction. It has structure. It has a kind of invisible landscape. That invisible landscape can push as well as pull. When opposite magnetic poles face each other, magnets attract. When like poles face each other, they repel. This happens because the fields around the magnets combine in different ways. In one arrangement, the combined field allows the magnets to move together into a lower energy state. In another arrangement, the magnets resist being pushed together. You can feel this resistance in your fingers when two small magnets refuse to meet. The sensation is gentle, but it is deeply revealing. You are feeling a field. In that moment, your hand is touching a principle that extends far beyond the room. Magnetism is not only a property of fridge magnets and metal tools. It is part of electromagnetism, one of the major interactions that organize the physical world. Electricity and magnetism are closely connected. Moving electric charge can create magnetism, and changing magnetic fields can create electric effects. This connection powers electric motors, generators, speakers, microphones, transformers, and much of the technology that quietly surrounds modern life. The feeling may be small, but the principle is not. A magnet shows how physical influence can live in space itself. This is one of the quiet lessons of field physics. Nature does not always act through visible contact. Sometimes it acts through conditions spread through the surrounding region, waiting for the right kind of matter to enter and respond. The magnet does not need to know where the paperclip is. The paperclip does not need to know why it moves. Both are simply part of the same field-shaped situation. But the same connection also reaches into space. Earth itself has a magnetic field. Our planet behaves, in a broad sense, like an enormous magnet because motion in its liquid outer core helps generate a global magnetic field. A compass responds to that field, which is why it can point the way across land or sea. The compass needle is a small magnet aligning itself with the much larger magnetic presence of the planet beneath it. That planetary field stretches far beyond the ground. It reaches into space and forms a vast region called the magnetosphere. This region interacts with charged particles streaming from the sun. Without this magnetic environment, those particles would meet Earth in a very different way. With it, many of them are guided, trapped, or deflected. Some are carried toward polar regions where they help produce auroras, those slow curtains of light that glow in the upper atmosphere. So the same basic phenomenon that moves a compass needle also helps shape one of the most beautiful sights on Earth. The connection grows even larger when we look at the sun. The sun is filled with electrically charged gas called plasma, and plasma is strongly shaped by magnetic fields. Sunspots, solar loops, flares, and huge eruptions from the sun all involve magnetic forces. These events can send charged particles across space toward Earth, where our planet's magnetic field becomes part of the story again. Magnetism links the small object in your hand with storms on the surface of a star. Farther out in the universe, magnetic fields become even more extreme. Neutron stars can carry powerful magnetic fields, and a special kind of neutron star called a magnetar holds the strongest known magnetic fields associated with any star. These are not gentle household magnets. They are collapsed stellar remnants, where matter and magnetic energy exist under conditions far beyond ordinary experience. Yet the word magnet still belongs there because the same physical theme continues: charged particles, fields, and invisible forces shaping matter across space. This is why a simple magnet is such a beautiful beginning. It is small enough to fit in your palm, but it points toward a universe filled with hidden structure. It teaches that reality is not limited to what the eye can see. The space around us can carry fields. Matter can respond across a distance. Quiet objects can reveal laws that also guide planets, stars, and the charged wind moving through the solar system. Even the familiar act of placing a magnet against a refrigerator becomes more interesting when seen this way. The magnet does not merely stick. It creates a field that interacts with the magnetic behavior of the metal beneath it. Inside that ordinary contact is a deep conversation between atomic structure and invisible force. The whole event is silent, stable, and easy to ignore. But if you pause for a moment, it becomes a doorway into physics. There is comfort in this, too. The world is full of hidden order, even in the smallest objects we barely notice. A magnet resting in your hand is quiet and undemanding. It simply reminds you that the universe is always present, even in ordinary things. So as the day loosens its hold, you can let this idea settle gently. Around you, unseen fields continue their patient work, steady and silent, while the night opens above them. Chapter 2. What magnetism really is. Magnetism begins with a simple idea that becomes stranger the longer you stay with it. Electric charge in motion can shape the space around it. This may sound distant from the small magnet on a refrigerator or the compass needle turning in a quiet room. Yet those familiar things are surface signs of a deeper relationship. Magnetism is not a separate kind of hidden substance inside certain objects. It is part of the behavior of electric charge, and electric charge is one of the basic features of matter. Wherever charge moves, a magnetic effect can appear. Wherever magnetic effects change, electric effects can appear as well. The two are woven together so closely that physicists speak of them as parts of one larger interaction called electromagnetism. To understand this gently, it helps to begin with charge itself. Some particles carry electric charge. Electrons carry negative charge, while protons carry positive charge. These words do not mean good or bad. They are names for two opposite ways matter can respond to electric and magnetic fields. Opposite charges attract, like charges repel. This electric behavior is already familiar in small moments, such as static cling or the tiny snap you may feel after walking across a carpet and touching a metal handle. Magnetism enters when charge is moving. An electric current in a wire is made from countless charged particles moving together through a material. Around that current, a magnetic field forms. If the current changes direction, the magnetic field changes direction too. This is one of the clearest ways to see that magnetism is connected to motion. A wire carrying current can behave like a magnet, and when that wire is wrapped into a coil, the magnetic effect becomes stronger and more organized. This is the basic idea behind an electromagnet. An electromagnet is useful because its magnetism can be turned on and off. When electric current flows, the field appears. When the current stops, the field fades. Cranes and scrap yards, electric motors, doorbells, speakers, and many other devices use this principle in different ways. They take the connection between electricity and magnetism and turn it into motion, sound, lifting power, or control. The world of machines is filled with this invisible partnership. But permanent magnets seem different at first. A permanent magnet does not need a battery connected to it. It does not need a visible wire. It can sit quietly on a table and still have a magnetic field. This raises the deeper question: where is the motion? The answer is inside matter itself. Atoms contain electrons, and electrons are connected to magnetism in more than one way. In older pictures of the atom, an electron is often imagined as moving around a nucleus, like a tiny planet around a star. That picture is useful only as a first step, because real atoms are governed by quantum physics. Electrons do not travel in simple little circular paths the way planets do. Still, their behavior inside atoms can carry angular momentum, and angular momentum connected with electric charge creates magnetic effects. Even more important is electron spin. Spin is one of the most confusing words in physics because it sounds like an electron is literally rotating like a tiny ball. That image can be helpful for a moment, but it is not exact. Electron spin is a quantum property. It has no perfect everyday picture. What matters here is that spin gives the electron a magnetic moment. A magnetic moment means that the electron behaves in some ways like a tiny magnet with a direction. This tiny magnetism is not added from outside. It belongs to the electron as part of its nature. The electron has charge, mass, and spin, and because of these properties, it can contribute to magnetic behavior. In most atoms, electrons are arranged so that their magnetic effects balance. They often pair in ways that cancel one another. When this happens, the material as a whole does not show strong magnetism, even though magnetic ingredients are still present deep inside it. This explains why magnetism can be everywhere in principle and selective in practice. Every ordinary object is made of charged particles. Every atom contains electrons. But a strong magnetic effect appears only when the internal magnetic contributions fail to cancel completely, and when many of those contributions cooperate. A magnet is therefore a sign of hidden order. Its field comes from countless tiny magnetic moments acting together rather than separately. The word field is essential, but it should be treated carefully. A magnetic field is not a cloud of particles spilling from the magnet. It is a condition of space around magnetic sources. If a moving charge enters that region, the field can exert a force on it. If a tiny magnetic moment enters that region, the field can try to turn it into alignment. This is why compass needles rotate. The needle is itself magnetic, and Earth's magnetic field exerts a turning effect that encourages the needle to settle along a particular direction. Magnetic force has an unusual character. An electric field can push or pull a charged particle along the direction of the field. A magnetic field acts on moving charge in a sideways way. The force depends on the motion of the charged particle and the direction of the magnetic field. Because of this, magnetic fields often bend paths rather than simply speeding particles up or slowing them down. Charged particles can spiral around magnetic field lines, which becomes important in many natural settings, including plasmas in space. There is another subtle point that makes magnetism different from many simple pictures. A magnet always has two poles. If you cut a bar magnet into smaller pieces, each piece becomes a smaller magnet with its own north and south pole. You do not get a lone north pole in one hand and a lone south pole in the other. In ordinary magnetism, the poles come together as part of the same field structure. Magnetic field lines form closed patterns, continuing through and around the magnet rather than beginning from a single isolated magnetic charge. This is why field lines are useful, even though they are drawings rather than physical threads. They help us imagine direction and strength. Where the lines are drawn close together, the magnetic field is stronger. Where they spread farther apart, the field is weaker. A compass would tend to align with the direction of the field at its location. Iron filings near a magnet arrange into curved patterns because each small piece becomes temporarily influenced by the field and turns accordingly. The deeper unity of electricity and magnetism became one of the great achievements of physics. Electric fields and magnetic fields are not independent strangers. They are different expressions of one electromagnetic field. A changing electric field can be associated with magnetism, and a changing magnetic field can be associated with electricity. This connection allows electromagnetic waves to exist. Light itself is an electromagnetic wave, with electric and magnetic aspects traveling together through space. That means magnetism is present in a much wider story than the behavior of metal objects. Whenever light crosses a room, whenever radio waves carry a signal, whenever heat radiates from a warm object, electromagnetic fields are involved. The magnetic part may not be something you feel with your hand, but it is part of the wave. The small magnet on a table and the light from a distant star belong to the same broad family of physical law. This also reveals why magnetism can feel so unintuitive. Our bodies evolved to understand surfaces, weight, warmth, pressure, and motion on ordinary human scales. We are good at noticing what touches us. We are less naturally prepared to imagine fields spreading through space, or quantum properties inside electrons, or electric and magnetic effects transforming into one another depending on motion. Magnetism seems mysterious because it asks us to think beyond direct touch. Yet the science does not remove the wonder. It makes the wonder more precise. A magnet is not a charm with a hidden will. It is matter whose internal charged particles and quantum properties have produced a lasting field. Its pull is not a trick. Its push is not an illusion. It is an ordinary piece of the electromagnetic world, made visible through iron, motion, alignment, and force. There is something beautiful in the fact that magnetism comes from both motion and order. Moving charge creates magnetic fields. Electron spin gives tiny magnetic moments. Atomic arrangements decide whether those tiny moments cancel or cooperate. A permanent magnet is what happens when the microscopic world keeps its orientation strongly enough for the large world to notice. The quiet pull you feel between a magnet and a piece of metal is the large-scale result of events far below sight. And this is why magnetism is such a powerful doorway into physics. It starts as a simple sensation in your fingers, then leads inward to electrons and outward to light. It connects the practical world of motors and generators with the hidden architecture of matter. It reminds us that everyday objects are never as simple as they appear. A magnet is small, but the explanation behind it reaches into quantum physics, electromagnetism, and the structure of space itself. So when you imagine a magnet now, try to picture more than a solid object with two ends. Imagine charged particles, tiny magnetic moments, and a field quietly extending beyond the material surface. Imagine invisible order becoming strong enough to move something you can see. In that quiet movement, the universe is revealing one of its most patient rules. Chapter 3. Why some materials become magnetic. A magnet teaches a quiet lesson about matter. Two objects can be made from atoms, yet only one of them may answer strongly to a magnetic field. This is why a refrigerator magnet clings to a steel door but slides helplessly down a wooden cabinet. It is why a compass needle turns easily, while a copper coin seems almost indifferent. It is why a nail can sometimes become temporarily magnetic, but a piece of glass does not behave in the same way. The difference hides far below the surface, inside the arrangement of electrons and atoms. All ordinary materials contain electrons, and every electron has properties that can contribute to magnetism. But most materials are magnetically quiet because their internal magnetic effects are arranged in a balanced way. The tiny contributions cancel one another so well that the object does not become a strong magnet. It may still respond very weakly to magnetic fields, but the response is usually too small for our senses to notice. To the human hand, the object simply feels neutral. This is true for many familiar substances. Wood, plastic, paper, water, and glass do not cling to an ordinary magnet. Some metals, such as copper, silver, and gold, also do not show the strong attraction people often expect from metal. Metal is not automatically magnetic. That is a useful distinction because everyday language often connects metal and magnetism too closely. A magnet does not love all metal. It responds strongly only to particular kinds of internal atomic order. The strongest everyday magnetic materials belong to a group called ferromagnetic materials. Iron is the best known example, and nickel and cobalt are also important. Gadolinium is another element that can become ferromagnetic near ordinary temperatures, though it is far less familiar in daily life. Many practical magnets are not made from pure elements alone. They are often made from alloys, where different elements are combined so the material has useful strength, stability, and resistance to losing its magnetism. The key reason these materials behave so differently is that many of their atomic magnetic moments can cooperate. Inside a ferromagnetic material, neighboring atoms interact in a way that favors alignment. Their tiny magnetic tendencies can point in the same direction across small regions. These regions are called magnetic domains. Each domain is already magnetized internally, even if the whole object does not yet act like a strong magnet. Imagine a large crowd of people standing in groups. Within each group, everyone faces the same direction. But different groups face different ways. From far away, the crowd as a whole has no single direction. This is similar to an unmagnetized piece of iron. It contains many organized regions, but those regions point in different directions, so the larger object does not show a strong outside field. When the material is placed in a strong magnetic field, some domains begin to change. Domains that are already pointing close to the direction of the applied field can grow. Other domains shrink. In some cases, the direction inside domains can rotate as well. The material is not being filled with magnetism from nowhere. The external field is helping the internal order choose one dominant direction. As more domains line up, the object becomes magnetized. This is why a simple iron nail can become magnetic after contact with a strong magnet. The nail already contains the ingredients for magnetic behavior. The outside magnet encourages many domains inside the nail to become better aligned. Afterward, the nail may pick up small metal objects for a while. Depending on the material, some of that alignment may fade quickly, or it may remain for a long time. The difference between temporary and permanent magnetism is connected to how easily the domains can move. In some materials, domain boundaries shift readily. These materials can be magnetized and demagnetized with relative ease. They are useful when magnetism needs to change quickly, such as in transformer cores or electromagnets. These are often called soft magnetic materials. The word soft does not necessarily mean physically soft to the touch. It means magnetically easy to change. Other materials resist changes in domain alignment. Once magnetized, they hold their internal order firmly. These are hard magnetic materials, again using hard in a magnetic sense. Permanent magnets are made from materials that keep their domain alignment stable after the external magnetizing field is removed. This stability is why a small permanent magnet can remain useful for years, quietly maintaining its field without needing power. The material's crystal structure matters as well. Atoms in solids are arranged in patterns, and those patterns influence how electron behavior spreads through the material. The spacing between atoms, the symmetry of the arrangement, and the way electrons occupy available states all affect whether magnetic moments prefer to align. Ferromagnetism is not caused only by the presence of certain atoms. It depends on how those atoms are held together in the solid. This is one reason alloys can be so powerful. By combining elements, engineers can create materials whose atomic arrangements support strong and stable magnetism. Neodymium magnets, for example, are made from compounds that include neodymium, iron, and boron. Their strength comes from the particular way their atoms and electrons work together. The result is a magnet far stronger than a simple piece of iron would be by itself. Temperature also plays an important role. Heat is motion inside matter. As temperature rises, atoms vibrate more strongly, and that thermal agitation can disturb magnetic order. A ferromagnetic material can lose its strong ferromagnetic behavior when heated above a certain point called the Curie temperature. Below that temperature, the material can maintain the cooperative alignment needed for ferromagnetism. Above it, the internal order is disrupted, and the material behaves much more weakly in a magnetic sense. This does not mean the atoms vanish or the electrons stop existing. It means the cooperative arrangement can no longer stay organized against the disorder produced by heat. If the material cools again, it may become capable of ferromagnetic order once more, though the exact magnetic state depends on its history and conditions. A magnet heated too strongly may lose much of its useful magnetism because the carefully aligned domains have been disturbed. Mechanical stress can matter too. Hammering, bending, or dropping certain magnets can disturb domain alignment. In older demonstrations, a steel needle could be magnetized by stroking it repeatedly with a magnet and then weakened by rough handling or heating. These simple examples show that magnetism is not only about chemical identity, it is also about history. How a material was formed, cooled, strained, and exposed to magnetic fields can affect how magnetic it becomes. Some materials respond to magnetic fields in gentler ways. Paramagnetic materials are weakly attracted to magnetic fields because they contain magnetic moments that can partly align while the field is present. But the alignment is usually small and easily disrupted by thermal motion. When the field is removed, the material does not keep a strong magnetization. Aluminum and oxygen can show paramagnetic behavior, though ordinary experience rarely makes this obvious. Diamagnetic materials respond in the opposite weak way. They are slightly repelled by magnetic fields. This effect is present in all materials, but in many substances it is hidden by stronger magnetic behavior. In materials where other magnetic effects are absent or very small, diamagnetism can be observed with sensitive equipment or extremely strong magnets. Water, graphite, and many organic materials are diamagnetic. The effect is real, though it is far too weak to notice with a common refrigerator magnet. These categories help explain why the world feels so selective around magnets. A magnet does not treat all matter equally. Some matter barely responds. Some responds weakly, only while a field is present. Some can become strongly magnetized and remember that state. The difference comes from electron arrangements, atomic interactions, crystal structure, temperature, and the ability of domains to move or remain fixed. There is a quiet elegance in this. A piece of iron and a piece of copper may look equally solid, equally ordinary, and equally metallic. Yet inside them, their electrons follow different patterns of order. In iron, the conditions allow neighboring magnetic moments to cooperate strongly. In copper, the internal arrangement leads to nearly complete cancellation of strong magnetic behavior. The difference is invisible from the outside, but it determines whether the material can become part of a magnet's pull. This is why magnetic materials feel like a hidden class of matter. They are not special because they break the rules. They are special because their inner rules line up in a rare and useful way. The magnetism we notice with our hands is the visible outcome of countless microscopic agreements. Tiny moments inside atoms settle into patterns, domains grow or shrink, and the object begins to carry an influence beyond its surface. So when a magnet sticks to a steel refrigerator door, the moment is more subtle than it seems. The magnet is meeting a material whose inner structure can answer. The steel contains iron, and iron has the kind of atomic order that can cooperate with a magnetic field. The attraction is a conversation between two pieces of matter carried by invisible structure and made possible by the quiet alignment of electrons. This chapter gives the everyday magnet a more material face. It is no longer only a field in space or a mysterious pull between objects. It is also a story of what matter is made of, how atoms are arranged, and how tiny magnetic tendencies can either cancel, briefly respond, or join together into something strong enough to feel. In that sense, a magnetic material is matter that has learned how to point in the same direction. Chapter 4. The field around a magnet. Around every magnet, space takes on a hidden shape, and that shape is what makes the magnet seem to reach beyond itself. You cannot see this shape directly. A magnet lying on a table looks like a small solid object with smooth sides and ordinary weight. The air around it appears unchanged. Light passes through the room as usual. Dust drifts as usual. Your hand feels no texture in the space beside it. Yet if you bring a compass close, the needle begins to turn. If you scatter fine iron filings over a sheet of paper above the magnet, the filings gather into curved paths. The empty-looking space has been carrying information all along. That organized region is the magnetic field. The field is a physical condition surrounding the magnet, a way in which space near the magnet can influence magnetic materials and moving electric charges. The magnet itself is the source, but the effect extends outward. The farther you move away, the weaker the field becomes. Yet close to the magnet, the structure can be strong enough to turn needles, pull iron, and make other magnets twist in your fingers. A field is one of the most important ideas in physics because it lets us describe action through space. Instead of imagining that objects must touch each other before anything can happen, a field allows the surrounding region to matter. A compass needle does not need to press against a magnet in order to respond. The needle sits within the magnet's field, and the field gives it a preferred direction. The effect is quiet and precise. At every point near the magnet, the field has a direction and a strength. The direction can be mapped with a small compass. Place the compass near one side of a bar magnet and the needle settles along a particular angle. Move it slightly and the needle changes direction. If you repeat this in many places, the directions begin to form a pattern. Connecting those directions gives the familiar curved lines seen in physics books and classroom demonstrations. These are called magnetic field lines. They are a drawing method, but they represent something real. The direction a tiny compass would tend to point at each location. Field lines help us think about the invisible. Outside a simple bar magnet, they are usually drawn as curves emerging from the North Pole and returning toward the South Pole. Inside the magnet, the pattern continues, completing closed loops. This closed-loop nature is one of the distinctive features of magnetic fields. The lines form continuous paths passing through and around the magnet as part of one connected structure. The closeness of the field lines tells us something too. Where the lines are crowded together, the magnetic field is stronger. Near the poles of a bar magnet, the lines are usually densest, so the magnetic effect is strongest there. This matches ordinary experience. The ends of a magnet tend to grip more strongly than the middle. A paperclip is more easily attracted near a pole because the field changes more intensely in that region. This change in field strength is part of what creates attraction. A piece of iron near a magnet becomes influenced by the field. Its internal magnetic regions respond, and the iron is pulled toward the area where the field is stronger. The surrounding field creates a situation in which the iron lowers the overall energy by moving closer. The result looks like a simple pull, but underneath it is a relationship between matter and the shape of the field. Two magnets reveal the field even more clearly. Bring opposite poles toward each other, and the magnets attract. Bring similar poles toward each other, and they resist. The feeling of resistance can be surprisingly physical. You push the magnets together, and an unseen pressure seems to build between them. Nothing solid fills the gap, yet your fingers feel a force. This happens because the magnetic fields of the two objects combine. In one arrangement, the combined field supports motion together. In another arrangement, the combined field makes that motion energetically unfavorable. The space between repelling magnets is especially useful for understanding that fields carry energy. When you press two similar poles together, your hand is doing work against the magnetic field. If you let go, the magnets move apart. The field stores and releases energy through the arrangement of the magnets. This is why magnets can move objects, spin motors, hold doors closed, and suspend certain objects in carefully controlled systems. A field can carry energy even when it cannot be seen. Iron filings make this hidden structure visible in a beautiful way, but they can also mislead if taken too literally. The filings do not show every part of the field. They gather into chains because each tiny piece becomes magnetized and interacts with its neighbors. The pattern they form is a visible response to the field, rather than the field itself. The real magnetic field fills the region continuously. The drawn lines are a guide for the mind, a way of representing direction and strength without claiming that space is divided into separate threads. This matters because a magnetic field has a value throughout the surrounding region, even between the lines we draw. If a compass is placed between two drawn field lines, it still turns. If a moving charged particle enters that region, it can still be deflected. The field is present throughout the region, while the curves are a simplified map, like contour lines on a map of mountains. The contour lines help you understand the shape of the landscape, but the mountain exists between them too. A magnetic field also has direction in a more subtle sense. A compass aligns along the field because the needle has its own magnetic orientation. The field exerts a turning effect, called a torque, on the compass needle. The needle settles when its own magnetic direction lines up with the local field. This is why a compass can be used as a field detector. It is a small object responding to the direction built into the space around it. Moving electric charges experience magnetic fields differently. A charge moving through a magnetic field can be pushed sideways. This is why magnetic fields often curve the paths of charged particles rather than simply pulling them forward. In space, this effect becomes extremely important. Charged particles can spiral around magnetic field lines, becoming guided by fields over enormous distances. Later, this same idea will help us understand Earth's magnetic shield, auroras, and solar storms. For now, the important point is simple. The field around even a small magnet teaches the same basic language used throughout space physics. The shape of a magnet affects its field. A bar magnet creates one kind of pattern. A horseshoe magnet bends the poles closer together, making the field between them stronger and more concentrated. A disk magnet spreads its field in another way. A ring magnet has its own geometry. The material and magnetization matter, but so does shape. Magnetic fields are spatial structures, so the form of the object helps determine the form of the surrounding influence. Distance matters as well. A magnet may feel strong when pressed against metal, yet its pull can fade quickly as the gap grows. This is why a refrigerator magnet holds firmly against the door but may fail through a thick book. The magnetic field weakens with distance, and the details depend on the shape of the magnet and the material nearby. This fading with distance is one reason magnetism feels local in ordinary life, even though magnetic fields can extend far beyond their sources. The field can also be redirected by certain materials. Iron and steel can guide magnetic fields because their internal structure responds strongly. This is why magnetic circuits are used in machines. The field can be concentrated through a chosen path, allowing devices to use magnetism more efficiently. In motors and generators, carefully shaped pieces of magnetic material help guide fields so that electricity and motion can exchange energy in controlled ways. The same invisible principle behind a paperclip moving toward a magnet becomes part of large machines that power modern life. A magnet's field is steady when the magnet is still, and its internal magnetization remains stable. But fields can change. Move a magnet near a coil of wire, and the changing magnetic field can create an electric effect in the wire. This is electromagnetic induction, one of the great practical discoveries in physics. It allows generators to produce electric current from motion. The field around a magnet is therefore more than a static halo. When its pattern changes through space and time, it can help create electricity. This gives the magnet a deeper meaning. The field around it is part of the physical reality of the object. A magnet includes its material body and the surrounding field through which it interacts. The boundary between object and environment becomes less simple. The magnet sits in one place, but its influence occupies a larger region. Its presence is felt beyond its surface. That idea prepares us for the cosmic scale. Around Earth, magnetic fields extend into space. Around the Sun, magnetic fields twist through plasma and shape storms. Around certain stars, magnetic fields become almost unimaginable in strength. These are grander versions of the same idea you can begin to understand with a bar magnet, a compass, and a few iron filings. Space can hold invisible structure. Fields can organize motion. Empty-looking regions can quietly guide matter. So the field around a magnet is a lesson in seeing without seeing. It asks you to trust patterns revealed by response. The compass turns, the filings curve, the paperclip moves, and your fingers feel resistance between two magnets. Each response is a clue. Together, they show that the space around a magnet is active, shaped, and physically meaningful. A small magnet does not simply occupy space. It gives space a direction. Chapter 5. Earth is a giant magnet. The magnetism of Earth is one of the most quietly important facts about our planet, because every compass needle is responding to a hidden engine far below your feet. When we say Earth is a giant magnet, it can sound as if a huge bar magnet is buried inside the planet. That image is useful for a first picture, because Earth has a broad magnetic north and magnetic south, and the field around the planet resembles the field around a simple magnet in several important ways. A compass needle turns because it is a small magnet trying to align with Earth's magnetic field. Yet the real story is far more interesting than a buried object. Earth's magnetism is produced by motion, heat, metal, rotation, and time. The source lies deep inside the planet, in a region no human has ever reached. Beneath the crust and mantle, Earth has a core made mostly of iron, with nickel and other elements mixed in. The inner part of the core is solid, held that way by enormous pressure. Around it is the outer core, a layer of liquid metal. This liquid outer core is crucial. It can move, flow, swirl, and carry electric current. Because iron is electrically conducting, its motion can help generate magnetic fields. This process is called the geodynamo. The word sounds technical, but the idea can be approached gently. A dynamo is a system that turns motion into magnetic and electric effects. Inside Earth, hot liquid metal moves because heat is escaping from the deep interior. Some heat remains from the planet's formation, and some comes from the slow cooling and changing of the core. As heat travels outward, it drives convection, which means warmer material rises while cooler material sinks. The whole planet is also rotating, and that rotation helps organize the moving metal into large patterns. Together, these motions allow electric currents and magnetic fields to sustain one another. This is different from the magnetism of a refrigerator magnet. A household magnet keeps its field because many microscopic magnetic regions remain aligned inside a solid material. Earth's main magnetic field is generated by the movement of conducting liquid metal. The deep interior is far too hot for ordinary permanent magnetism to survive on a planetary scale. Instead, Earth's field is active and continuously renewed. It is less like a frozen magnetic object and more like a slow, vast engine. That engine is hidden, but its effects reach the surface. A compass is one of the simplest ways to notice them. The needle is magnetized, and when it is free to turn, it settles along the local direction of Earth's magnetic field. For centuries, this made navigation possible over oceans, deserts, forests, and mountains. Before satellite navigation and electronic maps, a compass gave travelers a dependable relationship with the planet itself. It made the invisible field practical. A compass does not point exactly to the geographic North Pole in most places. Geographic north is defined by Earth's rotation, by the axis around which the planet turns. Magnetic north is connected to the magnetic field, and it lies in a different place. The angle between compass north and true geographic north is called magnetic declination. This angle changes depending on where you stand, and it also changes slowly over time. Navigators must account for it when precision matters. There is also another feature called magnetic inclination or magnetic dip. Earth's field does not lie perfectly flat along the surface. In many places, it tilts downward or upward into the planet. Near the magnetic equator, the field is nearly horizontal. Near the magnetic poles, the field points much more steeply into or out of the ground. A compass needle used for direction is usually balanced so it can turn horizontally, but the full magnetic field has this vertical character too. Earth's magnetism has three-dimensional structure. The magnetic poles themselves wander. They are not fixed points painted onto the planet forever. Their motion reflects changes in the flow of liquid metal inside the outer core. Over years and decades, measurements show that magnetic north shifts across the Arctic region. This wandering is one reason magnetic field models must be updated. The planet's magnetic field is stable enough to guide navigation, yet alive enough to change. These changes are usually slow from a human point of view. A person may never notice them directly in daily life, but over geological time, Earth's magnetic field can change dramatically. The magnetic poles have reversed many times in the deep past, with magnetic north and magnetic south switching places. A reversal does not happen overnight. It unfolds over long intervals, and the field becomes more complicated during the transition. The important point is that Earth's magnetic field has a history. It is not a rigid feature of the planet. It is a moving record of deep interior dynamics. We know this partly because rocks remember magnetism. When volcanic rocks cool, certain minerals inside them can lock in the direction of Earth's magnetic field at that time. Iron-bearing minerals, such as magnetite, can preserve a magnetic signature as they solidify. On the ocean floor, this has created patterns of magnetic stripes on either side of mid-ocean ridges, where new crust forms and slowly spreads away. Those stripes helped reveal the history of seafloor spreading and gave powerful support to plate tectonics. In a quiet way, Earth's magnetic field helped scientists read the motion of the planet's surface. This memory in rock is called paleomagnetism. It allows researchers to reconstruct earlier positions of continents, study ancient field reversals, and understand how Earth has changed over time. A magnetic field that begins in the deep core becomes recorded in cooling lava, buried sediments, and the ocean floor. The invisible engine leaves marks in stone. The field is strongest in some regions and weaker in others. Earth's magnetism is often compared to a tilted dipole, like a simple magnet placed at an angle inside the planet. This approximation is useful, but the real field is more uneven. Local rocks can add small magnetic variations near the surface. Larger irregularities arise from the changing patterns in the core. The result is a field that can be mapped, measured, and modeled, but never reduced perfectly to a simple drawing. Because the field changes, careful observation matters. Magnetic observatories around the world measure the direction and strength of Earth's magnetic field over long periods. Satellites also help map the field from above. These measurements are used for navigation, surveying, studying Earth's interior, and understanding the environment around the planet. Every new measurement adds to the picture of a magnetic field that is both ancient and constantly shifting. Earth's magnetic field also connects the ground beneath us with space above us. The field begins in the deep interior, rises through the surface, and stretches outward into the space around the planet. At the surface, it guides a compass. Farther out, it becomes part of Earth's interaction with the Sun. This outer story belongs to the next step of the journey, where the field becomes a shield and a boundary. For now, it is enough to notice that the same planet that carries mountains, oceans, forests, cities, and clouds also carries an invisible magnetic structure around itself. There is something humbling about this. The ground feels still beneath your feet, but far below, liquid metal is moving in darkness. Heat is escaping. The planet is rotating. Slow currents are weaving a magnetic field that reaches upward through rock, ocean, air, and sky. A compass needle on a table is responding to the motion of a hidden sea of iron thousands of kilometers below it. The small movement of that needle is a surface whisper from Earth's deep interior. Calling Earth a magnet is therefore both simple and profound. It is simple because the planet has a magnetic field with poles, direction, and measurable strength. It is profound because that field is generated by a living planetary process. Earth is not magnetized in the way a small permanent magnet is magnetized. It is magnetic because the planet is internally active. Its deep layers still carry heat, motion, and electrical conductivity. The field is one sign that Earth is a dynamic world rather than a cold, motionless sphere. This also explains why different planets can have very different magnetic lives. A planet needs the right internal conditions to maintain a global magnetic field. Conducting material must move in the interior, and the motion must be organized enough to sustain a dynamo. Some worlds have strong fields, some have weak fields. Some may have lost global fields they once possessed. Earth's magnetism is part of what makes our planet geologically and physically alive. The next time you see a compass, it may feel less like an old tool and more like a conversation with the planet. The needle turns because it is listening to a field created far below the surface. It points along a structure too large to see and too slow to hear. It reminds us that Earth has an interior life, hidden beneath every step. And as you rest with that thought, the world can feel a little steadier. Beneath the quiet evening, beneath streets and houses and sleeping fields, Earth's deep engine continues its patient motion. The planet turns, the metal flows, and its invisible field remains wrapped gently around the world. Chapter 6. The magnetic shield around the world. High above the air we breathe, Earth's magnetic field spreads into space as a vast protective region, quietly meeting the restless flow from the sun before it reaches the world below. This region is called the magnetosphere. It is shaped by Earth's magnetic field, but it is also shaped by the sun. If Earth were alone in calm, empty space, its magnetic field would spread more evenly around the planet, like the field around a simple magnet. But Earth is not alone. It moves through a stream of charged particles flowing outward from the sun. This stream is called the solar wind. It is made mostly of electrons and protons, and it carries its own magnetic field as it travels through the solar system. The solar wind never truly stops. Even when the sun looks quiet from Earth, it is still releasing particles into space. These particles are thinly spread compared with the air around us, but they move quickly and continuously. When they encounter Earth's magnetic field, the result is not a simple collision against a solid wall. The magnetosphere is a flexible magnetic environment. It bends, compresses, stretches, and shifts in response to the pressure of the solar wind. On the side facing the sun, Earth's magnetic field is pressed inward. On the night side, away from the sun, the field is drawn out into a long magnetic tail. This gives the magnetosphere a shape that is often compared to a comet. The rounded part faces the sun, while the tail extends far behind Earth into space. The planet itself sits inside this invisible cavity, protected by a structure made of fields and moving charged particles. The outer boundary of this region is called the magnetopause. It is the place where the pressure of the solar wind and the pressure of Earth's magnetic field come into balance. Outside that boundary, the solar wind dominates. Inside it, Earth's magnetic field is the stronger organizing influence. The boundary is not fixed like the surface of a stone. It moves inward and outward as the solar wind changes. When the solar wind becomes stronger, the magnetosphere can be compressed. When conditions ease, it can expand again. Farther ahead of Earth, in the direction of the sun, another important region forms. The solar wind moves faster than the speed at which certain disturbances can travel through it, so when it meets Earth's magnetic obstacle, a bow shock forms. This is similar in spirit to the wave that forms in front of a boat moving through water, though the physics involves plasma and magnetic fields rather than ordinary liquid. At the bow shock, the solar wind is slowed, heated, and disturbed before it flows around the magnetosphere. The word shield can make the magnetosphere sound like a hard shell. In reality, it is more like a living boundary of space weather. It protects by guiding, deflecting, trapping, and redirecting charged particles. Many particles from the sun are steered around Earth rather than moving straight into the atmosphere. Some particles become trapped in regions of the magnetosphere. Others enter along particular magnetic pathways, especially near the polar regions. The shield is powerful, but it is dynamic. This matters because charged particles carry energy. If large numbers of energetic particles reached the upper atmosphere and space around Earth without this magnetic organization, the planet's environment would be very different. The atmosphere itself is also an important layer of protection because it absorbs radiation and particles that reach it. The magnetic field adds another kind of protection above the atmosphere, reducing direct exposure to many energetic particles from space and shaping how solar activity affects the planet. Inside the magnetosphere are the radiation belts. These regions contain charged particles trapped by Earth's magnetic field. They are often called the Van Allen belts, named after the scientist associated with their discovery through early space measurements. The belts are not solid rings. They are regions where energetic particles spiral and bounce along magnetic field lines, remaining confined for some time. Their intensity can change as solar activity changes. For spacecraft, the radiation belts are important. Satellites passing through or operating near these regions must be designed with radiation in mind. Energetic particles can affect electronics, sensors, solar panels, and communication systems. Human spaceflight must also consider radiation exposure. The same magnetic environment that helps protect the lower atmosphere can create regions in space where trapped radiation becomes a hazard for technology and astronauts. This is one reason space weather forecasting exists. Weather on Earth involves wind, temperature, clouds, and storms in the atmosphere. Space weather involves solar wind, magnetic fields, energetic particles, and disturbances in the near-Earth environment. A strong solar eruption can send a disturbance toward Earth. If its magnetic orientation connects efficiently with Earth's magnetic field, energy can enter the magnetosphere more strongly. The result can be a geomagnetic storm. During a geomagnetic storm, currents and fields in Earth's space environment change. Satellites can experience increased drag if the upper atmosphere heats and expands. Radio communication can be disrupted. Navigation signals can become less reliable. Electrical systems on the ground can be affected during severe events because changing magnetic fields can induce currents in long conductors such as power lines. These effects remind us that the magnetosphere is not remote from human life. It is part of the environment our technology now depends on. Yet the magnetosphere is not simply a danger zone. It is also a great stabilizer. It helps Earth live inside the sun's influence without being fully exposed to every charged particle the sun releases. The sun gives Earth light and warmth, but it also sends plasma and magnetic disturbances through space. Earth's magnetic field does not shut the sun out. It negotiates with it. It creates a boundary where solar energy is partly deflected, partly stored, partly released, and partly guided. Near the polar regions, the magnetic shield opens into one of its most beautiful consequences. Earth's magnetic field lines guide some charged particles toward the upper atmosphere. When those particles interact with atoms and molecules high above the surface, light can be produced. This is the beginning of the Aurora story, which deserves its own quiet chapter. For now, it is enough to see that the magnetosphere does not simply block everything. It channels energy in ways that can become visible as glowing curtains in the sky. The shield also helps us understand why planetary magnetism matters when comparing worlds. A planet with a global magnetic field can interact with the solar wind in one way. A planet without such a field interacts differently. Atmospheres can still be protected by gravity, chemistry, thickness, and other factors, but a global magnetic field changes the relationship between a planet and its star. It creates a larger magnetic obstacle in space. Earth's magnetosphere is part of what makes our planet's space environment special among the rocky worlds. The magnetosphere is also a natural laboratory. Scientists study it with spacecraft that measure particles, fields, waves, and currents. These measurements show that the region around Earth is active and layered. There are boundaries, belts, sheets of electric current, waves moving through plasma, and sudden releases of stored energy. The magnetosphere may be invisible to our eyes, but to instruments, it is a complex landscape. One of the most important lessons is that fields can shape space on planetary scales. In earlier chapters, a small magnet showed how space near an object can acquire direction and structure. Around Earth, the same general idea becomes enormous. The magnetic field organizes a region much larger than the planet itself. It forms a cavity in the solar wind. It guides particles along curved paths. It stores energy and releases it during storms. It makes Earth's surroundings in space different from the interplanetary environment beyond. This changes the way the planet can be imagined. Earth is not just a sphere of rock, ocean, air, and life. It is surrounded by a magnetic presence that reaches outward into space. The surface is only one part of Earth's body. The atmosphere extends above us, and beyond that, the magnetosphere forms a larger invisible boundary. In a sense, Earth occupies more space than its solid globe suggests. It has a magnetic outline shaped by the sun. The shield is not perfect, and it does not need to be perfect. Some particles enter. Some radiation reaches near Earth space. Strong solar events can disturb the system. The magnetosphere changes constantly because it is part of an ongoing interaction. Its strength lies in its ability to respond. It bends under pressure, stores energy, releases it, and settles again. It is a shield made of motion, balance, and adjustment. There's a calm beauty in knowing this. Above the clouds and beyond the blue of the daytime sky, a vast magnetic structure is quietly working. It has no visible surface. It casts no ordinary shadow. Yet it stands between Earth and the streaming particles of the sun, shaping a safer region around the only home we have ever known. So when you picture Earth tonight, imagine more than a glowing planet suspended in darkness. Imagine a hidden magnetic shelter around it, soft in shape but powerful in effect. The solar wind flows around that shelter, the planet turns within it, and far below, life continues under a shield almost no one ever sees. Chapter 7. Auroras. When invisible fields become light. An aurora is one of the rare moments when Earth's invisible magnetic architecture becomes visible to the human eye. For most of the time, the magnetic field around our planet does its work silently. It guides charged particles, shapes the space around Earth, and responds to the changing wind from the sun without producing anything a person can see from the ground. Then, on certain nights, the hidden system reveals itself. Curtains of green, red, violet, or pale white light begin to move across the polar sky. They ripple slowly, brighten suddenly, fade into darkness, and return again as if the sky itself has begun to breathe. The beauty can feel dreamlike, but the cause is physical. Auroras happen when energetic charged particles enter the upper atmosphere and collide with atoms and molecules there. These particles are mostly electrons, though protons can also be involved. They are guided by Earth's magnetic field toward high-latitude regions, where the field lines connect more directly with the atmosphere. When the particles arrive, they transfer energy to the gases high above the surface. Those gases then release that energy as light. This process begins far above the glowing display. The sun constantly sends charged particles through space. Some of this energy becomes stored and rearranged in Earth's magnetic environment. During stronger disturbances, particles can be accelerated and sent along magnetic field lines toward the polar atmosphere. They do not simply fall straight down like rain. Their motion is shaped by magnetic fields, electric fields, and plasma waves in near-Earth space. By the time they reach the upper atmosphere, they carry enough energy to disturb the atoms and molecules they meet. The atmosphere at those heights is extremely thin compared with the air near the ground. It would not feel like breathable air. Yet it still contains oxygen and nitrogen, the two main ingredients involved in auroral light. When an incoming particle collides with an oxygen atom or a nitrogen molecule, it can push that atom or molecule into an excited state. This means the particle has given energy to the atom's electrons, lifting them into a higher energy arrangement for a short time. The excited atom or molecule then returns toward a lower energy state and releases the difference as a tiny packet of light. The color of the aurora depends on which gas is excited, how high the collision happens, and how the energy is released. The most familiar auroral color is green. This green usually comes from oxygen atoms in the upper atmosphere, often at altitudes around 100 kilometers above the surface. Oxygen can also produce deep red auroras at higher altitudes, where the air is thinner and excited oxygen has more time to release red light before another collision interrupts the process. Nitrogen contributes other colors. Depending on its state and the altitude of the interaction, nitrogen can help produce blue, purple, and reddish tones. Mixed together with oxygen light, these colors can create pink edges, violet lower borders, or pale white glows that look almost silver to the eye. The aurora is therefore a kind of atmospheric spectrum, painted by particles from space and the gases of Earth's upper air. The reason altitude matters is that the density of the atmosphere changes with height. Lower down, particles are closer together, so collisions happen more often. An excited atom may be disturbed again before it has time to release certain colors of light. Higher up, the air is thinner, and atoms can remain excited long enough for slower emissions to occur. This is why red auroras are often associated with higher altitudes, while green is more common at somewhat lower auroral heights. The sky is not simply changing color at random. Each color carries information about the height, gas, and energy of the event. Auroras usually appear near the polar regions because Earth's magnetic field guides particles more easily there. The magnetic field lines curve from space down toward the atmosphere near the magnetic poles, creating natural pathways. Around each pole there is an auroral oval, a ring-shaped region where auroras are most likely to occur. The oval can expand during strong geomagnetic activity, which is why people farther from the poles sometimes see auroras during powerful solar storms. This explains why the northern and southern lights are related. In the north, the display is called the aurora borealis. In the south, it is called the aurora australis. They are two expressions of the same planetary process, one in each hemisphere. Sometimes they can occur at the same time because both ends of Earth's magnetic system are involved. The planet is not lighting up in separate pieces. It is responding as one magnetic world. The shapes of auroras are as important as their colors. They can appear as quiet arcs stretching across the horizon, like pale bridges of light. They can become long curtains with vertical folds, as though a luminous fabric has been suspended from space. They can break into rays, spirals, patches, or pulsating clouds. Some displays move so gently that they seem almost still. Others brighten and shift quickly, creating waves that travel across the sky. These shapes come from the way particles move along magnetic field lines and the way energy is distributed in Earth's magnetic environment. A curtain often forms because many particles are traveling along neighboring magnetic field lines into the atmosphere. The vertical-looking rays trace the direction of those field lines from the viewer's perspective. The folds and ripples can reflect changes in particle flow, magnetic structure, and electric currents far above the ground. The sky becomes a screen on which invisible space processes are briefly projected. An aurora is often silent to the observer, but it is connected to powerful activity. The light itself is produced high above the surface, where the atmosphere is thin and the particles are energetic. The amount of matter involved is small compared with a weather storm in the lower atmosphere, yet the energy pathways stretch through enormous regions of space. A bright aurora may be the final visible sign of energy that was first carried outward from the sun, reshaped in Earth's magnetic tail, and released along field lines toward the atmosphere. This is why auroras are part of space weather rather than ordinary weather. Clouds, rain, and wind belong mostly to the lower atmosphere. Auroras belong to the upper atmosphere and near-Earth space. They are influenced by solar activity, magnetic conditions, and the flow of charged particles. A clear, dark sky may be necessary for viewing, but the cause of the light lies far beyond local weather. The aurora is Earth's sky responding to the sun. Auroras can also happen on other worlds. Any planet or moon with an atmosphere and a supply of energetic particles can, under the right conditions, produce auroral light. Jupiter has powerful auroras shaped by its enormous magnetic field and by charged particles in its environment. Saturn has auroras too. Mars, which lacks a strong global magnetic field like Earth's, can still show auroral glows when energetic particles interact with its atmosphere, though the patterns differ from Earth's polar displays. This makes auroras a cosmic phenomenon, not only an earthly one. On Earth, however, the sight carries a special emotional weight because it is visible from the ground. A person standing beneath an aurora can watch space physics unfold overhead. The display is both delicate and enormous. It seems close because it fills the sky, yet it happens far above where airplanes fly. It seems soft because the light moves like fabric, yet it is made by particles accelerated through a vast magnetic system. It feels ancient because humans have watched it for thousands of years, yet modern measurements show how deeply it belongs to plasma physics and solar-terrestrial interaction. The aurora also reminds us that the atmosphere is layered. The air around us feels familiar because we breathe it, feel it as wind, and watch it carry clouds. High above that familiar air, the atmosphere becomes thinner and more electrically active. It becomes a meeting place between Earth and space. There, atoms that are almost unimaginably sparse can still glow when struck by energetic particles. A small number of excited atoms spread across a huge region can become visible as a vast luminous band. There is a quiet paradox in that. The aurora looks like a flowing object, but it is made of countless separate emissions of light. Each tiny glow comes from an atom or molecule releasing energy after a collision. The curtain you see is the combined effect of these tiny events happening across the sky. What appears as one graceful motion is actually an immense pattern of particles, fields, and atmospheric gases working together. This makes the aurora one of the clearest bridges between the everyday and the cosmic. Earlier, a small magnet showed that invisible fields can move matter. Around Earth, those fields shape a magnetic environment. In the aurora, the same hidden structure finally becomes luminous. The field does not shine by itself, but it guides the particles that make the atmosphere shine. Invisible direction becomes visible color. For a sleep-focused journey through science, this is a gentle place to pause. The aurora does not ask us to see every particle or calculate every motion. It lets the eye receive the final result, light moving in silence above the turning world. Beneath it, Earth remains steady. Above it, the solar wind continues its long passage through space. Between them, the magnetic field quietly writes its patterns in the sky. So imagine the night far to the north or far to the south, cold and still, with stars scattered above a dark horizon. Slowly, a pale glow rises. It becomes green, then red at the edge, then violet near the lower folds. The light drifts without hurry, as if the planet is exhaling color into space. And for a moment, the invisible becomes visible, then fades gently back into the dark. Chapter 8. The Sun's Magnetic Storms. The sun looks calm from a distance, but beneath its steady golden light, it is a restless magnetic star, capable of twisting fields until they release energy across space. From Earth, the sun often appears simple. It rises, sets, warms the ground, lights the sky, and gives the rhythm of day. Its surface seems smooth to the unaided eye, a bright disk too intense to look at safely. Yet the sun is an immense sphere of plasma, a state of matter in which atoms are stripped into charged particles. Because plasma contains freely moving charged particles, it is deeply connected to magnetism. The sun's light reaches us as warmth and daylight, while its magnetic behavior reaches into the entire solar system. The visible surface of the sun is called the photosphere. It is the layer from which most of the sunlight we see escapes into space. On that surface, dark patches called sunspots can appear. They look dark because they are cooler than the brighter regions around them, though they are still intensely hot by earthly standards. Sunspots are signs of strong magnetic fields emerging through the solar surface. In a sunspot, magnetic fields interfere with the movement of hot plasma. Normally, heat rises from below through convection, carrying energy toward the surface. Where magnetic fields are especially strong, they can suppress some of that upward motion, making the region cooler and darker compared with its surroundings. A sunspot is therefore a visible clue that magnetic fields beneath and above the surface are becoming concentrated and complex. Sunspots often appear in pairs or groups with different magnetic polarities. They are like markers showing where magnetic field lines enter and leave the solar surface. Around them, bright loops of plasma may rise into the sun's outer atmosphere, following magnetic arches. These loops can be enormous, stretching far above the visible surface. They glow because the plasma in them is hot and energized. To instruments that observe the sun in certain wavelengths, the star appears covered in loops, arcs, and tangled magnetic structures. The sun rotates, but it does not rotate like a solid object. Its equator turns faster than its polar regions. This difference matters because the sun's magnetic field is embedded in moving plasma. As different regions rotate at different speeds, magnetic fields can become stretched and twisted. Over time, the field can grow complicated, like invisible threads being wound tighter and tighter. The sun's magnetic surface is therefore always changing, carried by plasma motion and shaped by rotation. The sun also follows a magnetic activity cycle that lasts about 11 years on average. During quieter parts of the cycle, sunspots are fewer and large eruptions happen less often. During more active parts, sunspots become more numerous, and solar flares and coronal mass ejections become more likely. Near the peak of this cycle, the sun's global magnetic field reverses, with magnetic north and magnetic south switching places. The sun is slowly reorganizing its magnetic identity. A solar flare is a sudden release of energy in the sun's atmosphere. It happens when stressed magnetic fields rapidly rearrange, releasing energy into light, heat, and accelerated particles. The key process is called magnetic reconnection. Magnetic field lines in plasma can become forced into new arrangements. When that happens, stored magnetic energy can be converted into particle motion and radiation. The result can be a flash of intense emission across a wide range of wavelengths. A flare may last minutes to hours, depending on its size and complexity. From Earth, it can affect the upper atmosphere almost immediately because its radiation travels at the speed of light. Strong flares can disturb the ionosphere, the electrically active region high above the surface. This can interfere with radio communication and certain navigation signals, especially on the sunlit side of Earth. The effect is electromagnetic radiation changing the behavior of the upper atmosphere. A coronal mass ejection is different from a flare, though the two can happen together. It is a large eruption of plasma and magnetic field from the sun's outer atmosphere, called the corona. Instead of being only a flash of radiation, it is a huge cloud of material moving outward through space. It can carry billions of tons of solar plasma and an embedded magnetic field. Some move more slowly than the usual solar wind. Others rush outward at tremendous speeds. When a coronal mass ejection is directed toward Earth, it may arrive after a period of travel through interplanetary space. If its magnetic field is oriented in a way that connects strongly with Earth's magnetic field, it can transfer energy into Earth's magnetic environment. This can produce a geomagnetic storm. The effects may include brighter auroras, disturbed satellite operations, changes in the upper atmosphere, radio disruptions, and induced currents in long electrical systems on the ground. Solar storms are magnetic events before they are anything else. The sun's plasma is tied to magnetic fields, and those fields store energy. When the magnetic structure becomes unstable or reconnects into a new arrangement, energy is released. Sometimes that release appears as a flare. Sometimes it lifts a huge cloud of plasma into space. Sometimes both occur as part of the same active region. The solar wind carries the sun's magnetic influence outward all the time. It is a stream of particles carrying magnetic fields through the solar system. Because the sun rotates, the solar wind and magnetic field form a large spiral structure in interplanetary space. Earth moves through this extended magnetic environment constantly. Most of the time, the interaction is manageable and quiet. During storms, the connection becomes more energetic. Solar storms are watched carefully because modern life reaches into space. Satellites orbit above the thick protection of the lower atmosphere. Astronauts travel through environments where radiation matters. Radio systems, navigation systems, power grids, and communication networks can all be affected by severe space weather. A strong solar storm is not a reason for panic in ordinary daily life. but it is a serious natural phenomenon that engineers and scientists must understand. The sun gives us a useful reminder here. The same star that sustains life also produces a changing space environment. Its warmth allows liquid water and climate. Its light feeds plants and drives weather. Its magnetic storms remind us that a star is not a passive lamp. It is a physical system in motion, filled with charged particles, rotating plasma, and magnetic fields that can suddenly release stored energy. Solar storms also help explain why magnetism is a cosmic force rather than only an earthly curiosity. In earlier chapters, magnetism appeared as the pull of a small object, the hidden order inside certain materials, the field around a magnet, and the deep engine of Earth. Here, it becomes stellar. Magnetic fields rise from a star, twist through plasma, and throw energy into space. The scale changes enormously, but the basic connection remains. Charged particles and magnetic fields shape one another. The sun's corona makes this especially striking. The corona is the sun's outer atmosphere, stretching far into space and reaching temperatures much higher than the visible surface. It is filled with plasma guided by magnetic structures. During a total solar eclipse, the corona can be seen as a pale halo around the darkened sun. Its shape changes with the solar cycle, becoming more complex when the sun is magnetically active. This faint outer glow is the region where many large eruptions begin. Coronal holes add another part of the picture. These are regions in the corona where magnetic fields open outward more freely into space, allowing faster solar wind to escape. When streams from coronal holes reach Earth, they can disturb Earth's magnetic environment, especially if conditions align. They are often less dramatic than major eruptions from active sunspot regions, but they show that the sun's magnetic influence is continuous. Space weather also comes from the changing shape of the sun's magnetic openings. The most powerful solar events in recorded history remind us that the sun can produce storms far stronger than the usual daily fluctuations. Large events can push auroras to lower latitudes and disturb technology. In the modern world, with satellites and electrical networks, understanding such events is increasingly important. Scientists observe the sun with spacecraft and ground-based instruments to follow sunspots, measure solar wind, detect eruptions, and estimate how disturbances may affect Earth. There is still much to learn. The details of how magnetic energy builds up and releases in active regions are complex. Predicting exactly when a flare will occur, how powerful it will be, or whether an eruption will strongly affect Earth remains difficult. The sun is near enough to study in great detail, yet complicated enough to keep surprising us. Its magnetic storms are both familiar and mysterious, part of the daily life of our star. At this point in the journey, the important feeling is scale. The important feeling is scale. A magnet on a table lets you sense a small field with your fingers. The sun shows what fields can do when they are woven through a star. They can darken regions of the surface into sunspots. They can guide glowing loops of plasma. They can store energy for days or weeks, then release it in sudden flashes and vast eruptions. They can send disturbances across the space between worlds. And still from the ground, the sun may look unchanged. A clear morning arrives. Light enters the room. Shadows form gently on the wall. The star above us continues its immense magnetic life, mostly hidden behind ordinary daylight. Its storms rise and fade across a surface too bright for the eye, while Earth turns quietly beneath its protective field. So as the chapter settles, Imagine the sun as a source of light and a living magnetic landscape. Beneath the calm disk in the sky, fields twist, loops glow, and plasma moves in slow, powerful patterns. Far away, Earth receives the light, keeps its orbit, and rests inside the larger breathing weather of a star. Chapter 9. Magnetars, the strongest magnets in the universe. A magnetar is what happens when magnetism is carried to an almost unimaginable extreme inside the collapsed heart of a dead massive star. To understand a magnetar, it helps to begin with a neutron star. A neutron star forms after a massive star reaches the end of its life and its core collapses. The outer layers may be thrown outward in a supernova, while the central core is crushed into an object far smaller and denser than any ordinary star. A neutron star can contain more mass than the Sun inside a sphere only about the size of a city. Matter there is squeezed so tightly that atoms lose their familiar structure. Electrons and protons are forced into new arrangements, and the object becomes dominated by neutrons, along with other extreme forms of matter under conditions we cannot reproduce on Earth. A magnetar is a special kind of neutron star with an exceptionally strong magnetic field. Ordinary neutron stars already have magnetic fields far beyond anything in daily life. Magnetars go much further. Their fields can be hundreds or thousands of times stronger than those of many other neutron stars. Compared with Earth's magnetic field, the difference is almost impossible to picture. The field of a magnetar can be trillions upon trillions of times stronger than the field that turns a compass needle. This does not mean a magnetar is large. In fact, its small size is part of what makes it so extreme. A massive stellar core collapses into a compact object, and during that collapse, rotation, magnetic field, and matter are forced into a much smaller volume. If the newborn neutron star rotates rapidly and its interior motions are intense enough, a powerful magnetic field may be amplified. The full details are still an active area of research, but the basic idea is that the birth of a magnetar involves collapse, extreme density, rapid motion, and magnetic field growth during one of the most violent transitions in stellar life. The result is a star where magnetism is not a gentle background feature. It becomes one of the dominant sources of energy in the star's outer behavior. In ordinary stars, light is powered mainly by nuclear fusion. In neutron stars, the original heat of formation, rotation, and magnetic fields can all matter in different ways. In magnetars, the decay and rearrangement of the magnetic field can power bursts of high-energy radiation. The star shines and erupts because its magnetic field is changing, stressing, and releasing energy. The surface of a magnetar is not like the surface of a normal star. A normal star, such as the Sun, is made of hot plasma with no solid crust like a planet. A neutron star is different. It can have a solid outer crust over incredibly dense interior material. That crust is thin compared with the whole star, but it is extremely strong. Under the influence of a magnetar's enormous magnetic field, the crust can be placed under great stress. As the magnetic field shifts, twists, or rearranges, it can strain the crust until it cracks or suddenly adjusts. These sudden events are often called starquakes. The word is useful because it suggests a comparison with earthquakes, but the scale and environment are completely different. In an earthquake, rock breaks or slips inside a planet. In a magnetar, the crust of a compact stellar remnant can shift under magnetic stress. When that happens, energy can be released into the surrounding magnetosphere, the magnetic environment around the star. This energy can appear as intense bursts of X-rays and gamma rays. Most magnetars are discovered because of these high-energy signals. They may spend long periods in a relatively quiet state, then suddenly produce bursts. Some bursts are short and repeated. Rarely, magnetars can produce giant flares, enormous releases of energy that can be detected across vast distances. These flares are among the most powerful magnetic events known. They reveal that a magnetar's field is not only strong, but also unstable enough to store and release tremendous energy. A magnetar also rotates. Many known magnetars spin once every several seconds, which is slow compared with some rapidly spinning neutron stars. Their rotation gradually slows down because the magnetic field carries energy away from the star. In a sense, the magnetar is breaking itself through its own magnetic influence. By measuring how quickly its spin changes, scientists can estimate the strength of its magnetic field and understand part of its evolution. This slowing is important because it shows that the magnetic field is not a decorative feature. It affects the star's life. A young magnetar may be more active, with a stronger magnetic field and more frequent eruptions. Over time, as magnetic energy is lost or rearranged, the star may become quieter. The most dramatic magnetar phase may last only a relatively short part of the neutron star's life, though the object itself can remain long after its strongest activity fades. The magnetic field near a magnetar is so extreme that normal intuition fails. Near the star, atoms would be distorted by the field. Matter would behave in ways unfamiliar from ordinary chemistry. The vacuum near the star can also be influenced by the field, because at such strengths even empty space is affected through quantum processes. These are not effects a person would ever encounter safely. They belong to a regime where gravity, magnetism, dense matter, and high-energy radiation meet. Still, magnetars are not cosmic monsters roaming through space in a threatening way. They are rare objects, usually very far away. Their danger is local to their extreme environments, while their scientific value is enormous. They allow us to study physics under conditions beyond any laboratory. The light they send across space carries information about dense matter, magnetic field behavior, particle acceleration, and the death of massive stars. Magnetars also connect to one of the larger questions in astronomy: how many kinds of neutron stars exist, and how do they change with time? Some neutron stars are seen as pulsars, sending beams of radiation that sweep across space as the star rotates. Some are quiet and difficult to observe. Some behave as magnetars, releasing energy from intense magnetic fields. These categories may not be completely separate. A neutron star's appearance can depend on its age, magnetic field, rotation, temperature, and history. Magnetars may represent one extreme path in the broader family of neutron stars. Their births are tied to supernovae, the explosive deaths of massive stars. When a massive star runs out of the fuel needed to support its core, gravity takes over. The core collapses, and the outer layers can be blasted outward. In some cases, the compact remnant left behind becomes a neutron star with an unusually strong magnetic field. The supernova spreads heavy elements into space, while the remnant remains as a dense magnetic ember. A magnetar is therefore both an ending and a beginning, the end of a massive star's ordinary life, and the beginning of a strange compact object ruled by magnetic energy. This connection makes magnetars part of the cosmic recycling story. Massive stars forge elements, explode, enrich space, and leave behind remnants. Some remnants become black holes. Some become neutron stars. a few become magnetars. The iron in a planet, the oxygen in air, and the calcium in bone all belong to the larger history of stars, while magnetars show what can happen when a stellar core survives collapse as one of the most extreme objects in the universe. Magnetars also remind us that magnetism is not confined to quiet, delicate effects. Earlier in this journey, magnetism appeared as the pull of a household magnet, the hidden order inside materials, Earth's field, and the sun's storms. A magnetar takes that theme to its limit. Here, magnetism can shape the crust of a star, power eruptions, accelerate particles, and send high-energy light across the galaxy. The same broad physical force that moves a compass needle becomes, under extreme conditions, a driver of stellar violence. Yet there is a strange calm in understanding them from far away. We are not standing near a magnetar. We are receiving faint signals that have crossed interstellar space. A burst that began in an object only about the size of a city may travel for thousands of years before reaching our instruments. By the time we notice it, the event itself is long over. The star has already moved on in its dark and silent life. This distance allows magnetars to become less frightening and more profound. They are reminders that the universe contains extremes our senses were never built to imagine. Matter can be crushed into densities beyond ordinary comprehension. Magnetic fields can become strong enough to reshape the environment around a dead star. Energy can be stored invisibly, then released in sudden flashes. And through all of this, physics remains the language that lets us make sense of the impossible-looking sky. So when you think of a magnetar, do not picture only destruction or brightness. Picture a small, dense remnant turning slowly in deep space, wrapped in a magnetic field of immense strength. Its crust may be under tension, its field may be shifting, its light may come in quiet pulses, then sudden bursts. It is a star after a star, a compact memory of collapse, still carrying the power of magnetism into the dark. And as the thought settles, it can make the night feel wider and quieter. Somewhere far away, magnetic stars turn in silence, while here, beneath Earth's gentle field, the world remains calm enough to rest. Chapter 10. A universe written in invisible fields. By the end of this journey, a magnet no longer feels like a small household object because it has become a doorway into the hidden architecture of the universe. The first lesson was simple enough to hold in your hand. A magnet can move a piece of metal through empty-looking space. Then the lesson widened. Inside matter, tiny magnetic tendencies can align. Around a magnet, a field gives space a direction. Deep inside Earth, moving liquid metal helps generate a planetary field. Around Earth, that field stretches outward and becomes a shield. In the upper atmosphere, invisible pathways can become auroras. On the sun, magnetic fields twist through plasma and release storms. In magnetars, magnetism reaches one of its most extreme known forms. Now the story becomes broader and quieter. Magnetism is not limited to objects we can pick up, planets we can stand on, or stars we can see in the sky. Magnetic fields thread through space itself. They exist between planets, between stars, inside galaxies, and in the vast regions where gas, dust, radiation, and charged particles drift through darkness. The universe is not an empty stage filled only with bright objects. It is crossed by fields that shape motion, guide particles, influence clouds, and carry energy across enormous distances. This does not mean every part of space is strongly magnetic. In many cosmic regions, magnetic fields are extremely weak compared with the field near a common magnet. Yet size matters. A very weak field spread across a galaxy can still become important because it acts over immense distances and long periods of time. A tiny influence, given enough space and time, can help guide the behavior of matter. Between the stars lies the interstellar medium. It is made of thin gas, dust, cosmic rays, and radiation. To human senses, it would seem emptier than any vacuum we can easily imagine. Yet it is not nothing. It contains atoms, charged particles, and magnetic fields. These fields affect the motion of charged particles, help shape clouds of gas, and interact with turbulence inside the galaxy. The space between stars is therefore active in subtle ways. Magnetic fields are especially important because much of the universe is plasma. Plasma is matter in which electrons and ions move freely enough for electric and magnetic effects to matter strongly. Stars are plasma. The solar wind is plasma. Many nebulae contain plasma. Gas around young stars and energetic regions of galaxies can behave as plasma too. Wherever plasma moves, magnetic field be carried, stretched, twisted, and strengthened. The field and the charged matter influence each other, creating patterns that can be delicate, chaotic, or enormous. In star-forming regions, magnetic fields can help shape the collapse of gas and dust. Stars are born when parts of cold interstellar clouds become dense enough for gravity to pull matter inward. Gravity is the main force driving collapse, but magnetic fields can affect how the gas moves. They can resist certain motions, guide flows, and influence how material gathers into dense cores. They do not stop star formation everywhere, yet they can help decide the pace and structure of the process. This makes magnetism part of the story of stellar birth. A star begins in a cloud that is threaded by fields. As material collapses, rotates, and forms a young star, magnetic fields can help launch jets, remove angular momentum, and shape the surrounding disk of gas and dust. These early environments are complex, but the central idea is grounded. Magnetic fields help charged matter move in organized ways. They can carry energy and direction through regions that gravity alone does not fully describe. Cosmic rays give another example. Cosmic rays are high-energy particles traveling through space, many of them moving at speeds close to the speed of light. They are often charged particles, which means magnetic fields can bend their paths. Because of this, a cosmic ray arriving at Earth does not necessarily point straight back to the place where it began. Galactic magnetic fields can scatter and redirect these particles many times during their journey. The universe becomes a maze of invisible curves. This is one reason studying cosmic rays is difficult. They may be born in violent places, such as supernova remnants, where shock waves and magnetic fields can accelerate particles to enormous energies. But by the time those particles reach our instruments, magnetic fields may have bent their paths again and again. Their arrival carries information, but the route has been shaped by the magnetic landscape of space. Galaxies themselves have magnetic fields. Spiral galaxies, including our own Milky Way, contain magnetic structures that can follow broad patterns through their disks and halos. These fields are weak in ordinary human terms, but they interact with gas, cosmic rays, and turbulence across galactic scales. They may influence outflows from galaxies, help shape the movement of charged particles, and contribute to the long evolution of galactic environments. How galaxies generate and maintain their magnetic fields is still an active scientific question. The broad idea involves motion in conducting gas, rotation, turbulence, and processes that can amplify weak seed fields over time. This resembles, in a loose way, the idea of a dynamo, though the environment of a galaxy is very different from the liquid metal core of Earth. The important point is that magnetism is not an afterthought in galaxies. It is part of the physics of how matter and energy move through them. Beyond individual galaxies, magnetic fields may also exist in galaxy clusters, and possibly in the thin material between clusters. These fields are harder to measure and understand because they are faint and spread across huge distances. Scientists study them through the way they affect light, radio waves, and charged particles. The larger the scale becomes, the more challenging the evidence becomes, yet the pattern remains suggestive. Magnetism appears again and again wherever the universe contains charged matter in motion. Measuring cosmic magnetic fields requires indirect methods. In ordinary life, we can use iron filings or a compass. In space, astronomers use light itself. Certain kinds of light from dust grains, gas, and charged particles can reveal the direction of magnetic fields. Radio waves can carry signatures of fields they have passed through. Polarization, which describes the orientation of light waves, can act like a clue. The field remains invisible, but its effects leave patterns that instruments can detect. This is a beautiful scientific theme. Much of the universe is known through response. We do not touch a magnetic field between stars. We watch how matter moves, how radiation changes, how particles are guided, and how light is polarized. The universe leaves traces of its invisible structures. Science becomes a careful reading of those traces. Magnetism also changes how we think about emptiness. Empty space in the everyday imagination is a blank absence. In physics, even regions with very little matter can have fields. Space can contain gravitational fields, electromagnetic fields, radiation, and particles passing through it. The cosmic void is quiet, but it is not a simple emptiness. It has conditions. It has history. It can carry influences from distant stars, galaxies, and ancient events. This does not make the universe mystical. It makes it richer. The invisible fields of physics are measurable, testable, and deeply connected to matter. They are not hidden intentions or secret messages. They are natural structures described by careful observation and physical law. A field is one of the ways reality keeps track of how things can affect other things across space. That idea brings us back to the small magnet. The magnet in your hand was never separate from the larger story. It was a local, touchable expression of a universal principle. It showed that space can be structured. It showed that matter can respond before contact. It showed that direction, energy, and influence can exist where the eye sees nothing. Earth expanded the lesson into a planetary scale. The sun expanded it into stellar weather. Magnetars carried it into the extremes of collapsed stars. Galaxies and interstellar clouds now widen it into the quiet architecture of cosmic space. At each scale, the same broad theme returns in a new form. Charged matter moves, fields arise, fields guide matter. Energy is stored, released, and carried onward. There is comfort in seeing the universe this way. It is not a collection of isolated objects floating through emptiness. It is a connected physical environment, filled with relationships that are often unseen but never meaningless. A planet is connected to its star through light, gravity, particles, and fields. A star is connected to its galaxy through gas, motion, and magnetic structure. Even the space between things participates in the story. For a tired mind at the end of the day, this can be a gentle thought. The universe does not need to be loud to be active. Its deepest structures often work silently. Fields stretch through darkness without asking to be noticed. Particles follow curved paths. Stars form inside cold clouds. Galaxies turn slowly, carrying weak magnetic patterns through their wide arms. And here, in the quiet of one small world, we can notice the same principle in a magnet on a table. The ordinary object becomes a reminder that reality has layers. Beneath the visible surface, there is order. Around every familiar thing, there may be a deeper connection to the laws that shape worlds and stars. So let the image soften now. A small magnet rests in a quiet room. Earth turns inside its magnetic shelter. The sun breathes plasma and light through the solar system. Far away, galaxies carry faint magnetic threads through oceans of darkness. Nothing needs to hurry. The fields remain, patient and unseen, writing their gentle lines through the universe. And now, my friend, we've reached the end of this quiet journey through magnetism. We began with a simple object in the hand, something small enough to place on a table or hold against a refrigerator door. But from there, the story opened outward. We found invisible fields inside matter, around Earth, across the solar wind, inside auroras, through the storms of the sun, and finally around magnetars, where magnetism becomes one of the strongest forces a star can carry. Maybe that is the gentle wonder of physics. The universe does not always reveal itself through distant galaxies or dramatic explosions. Sometimes it begins with something ordinary, a small magnet, a compass needle, a quiet pull through empty-looking space. So if you are still awake, you can drift into another Orbital Dreams journey and keep exploring the universe a little longer. And if sleep is already close, let the night take you softly. Sweet dreams among the stars.